Hello and welcome to section 1 of CSE 373. Since this is our first video section, please make sure to have this section 1 handout either pulled up in front of you or printed out to do practice problems during the section, as well as the rest of the problems we don't cover in this video for further practice. In this section, we'll cover administrivia or course logistics, briefly review reference semantics, and then practice implementing some methods of ADTs. Let's hop into it. Starting with administrivia, as Casey said in lecture, the major course topics of CSE 373 are data structures and ADTs, graphs and graph algorithms, algorithm analysis, and sorting. 373 is a direct continuation of the intro series, and these are the rest of the topics you'll need to pass almost any technical interview. There are three major components in CSE 373. The first one are projects. There will be 5 programming projects during the quarter, P0 through P4, and these projects are completely auto-graded. Your final score is determined by Gradescope, the auto-grader. And you may work with a partner on all of these programming projects except for the first one, P0. You may work alone, but we highly encourage working with a partner. It not only lessens your individual workload, but we find that this allows groups to get through programming projects quicker and also have a deeper understanding as you're able to bounce ideas off of each other. The second main component of 373 are exercises. There will be 7 individual exercises throughout the quarter, exercise 1 to exercise 7, and these are written assignments. Finally, there will be 2 exams, a midterm and a final, held during lecture. So make sure to be in lecture on those days to avoid missing out. Continuing with course logistics, you'll have 5 late days to spend throughout the quarter on any projects or exercises that you need to use them on. And these late days allow you to submit assignments up to 24 hours late without penalty. So this means if you need to turn in a project 1 hour after the initial deadline, you unfortunately have to use 1 of your 5 late days. Here is the grading breakdown for the course, and you can see GPA guarantees on the course syllabus on the website. Finally is the golden rule of section. Please don't be afraid to ask questions. This not only makes quiz sections more fun for you and the TA, right? Everyone hates a dead section, but this allows us to directly answer any questions you have and make section more valuable as we can directly tailor quiz sections to your needs. Awesome, so please ask questions. Use the Ed board if you have any questions outside the section, and a TA will get back to you. If it's a private matter that you don't want other students to see, make sure to mark the Ed post as private. And if it really is a private question that you only want maybe your quiz section TA or Casey to see, then make sure to email them directly. Finally, section videos like this will be posted to the course website in Canvas in case you are unable to make it this section. However, you should, in italics, still come to section. We really mean this. There are so many in-person learning opportunities that you will miss if you consistently skip, right? Like I said earlier, in-person quiz sections allow you to interact with other students and with the TA directly face-to-face. So us, the TAs, can answer your questions and maybe give you a more in-depth answer than posting only on Edboard and staying at home. And by coming to section, you are forced to participate in active learning, which allows you to more deeply understand the content by working through it with your TA and with the other students. And as Casey said in lecture, students who consistently come to section tend to do much better on in terms of their final grade than students who skip. Cool. Let's hop into reference semantics review. So to review reference semantics, we'll run through some code and then demonstrate what memory looks like via some memory diagrams. So code will be underlined, and the underlined line of code will have just been executed. We will have just run the line of code, and the memory diagram will be updated as follows. Code for main that is run will be underlined in red, while code and functions called by main will be underlined in blue. Let me move this camera over. There we go. Cool. So here we have 2 methods, foo and our main method. We have a memory diagram to the top right. So in main, notice we have three variables, x, y, and z. And this is represented in our memory diagram. Notice though, these variables are stored slightly differently. X is an int, while y and z are int arrays. An integer is a primitive data type, so we directly store that value inside of our variable. So we store the value 1 inside of x. However, y and z are int arrays. These are objects and are much bulkier than primitives. So instead of creating and storing an entire array inside of our variable, instead we store a reference or the address of these arrays somewhere in memory inside of our variable. So y and z store a reference or kind of a pointer to these arrays instead of the actual array itself. So now we call foo, and then foo is inside of foo has its own scope with its own x, y, and z values separate from main. They're still connected as we'll see. So foo takes in three parameters, an int x, an int array y, and an int array z. Since x, the parameter x is once again a primitive, we'll copy and store the value of the x we pass in from main. So the x inside of foo receives a copy of that one since it's a primitive. However, since we store int arrays via references, when we pass our y and z from main into foo, the y and z inside of foo will receive a copy of that reference or that address to the arrays that reference inside of main. So now the foo y will refer to the same array that main y refers to, and the same for z. They point to the same arrays. Next, when we set x is equal to 2, we simply just change the value that's stored inside of foo's x to 2. And notice that the main x is unchanged. And then when we set y to be equal to a new int array, since y is an int array, an object that's stored by reference, we just change the reference to point to a newly created int array somewhere in memory. And once again, the main int array is unchanged, or the main y array. Cool. And after foo executes, its scope and everything else disappears, and the array that we just created, as well as those other variables, will be eaten up by Java's garbage collector, and the memory will be cleared. Great. Now hop over to your worksheet and do problem 1.1a. So pause the video here, and then unpause the video once you've completed the problem. Alrighty. If you're at this point, I'm assuming you have at least attempted problem 1.1a from the worksheet. So this problem deals with reference semantics. And a major tip is to always draw out the variables and references on these sorts of problems. Much like linked list programming problems, by drawing out references in reference semantic problems, you can more clearly see what's actually going on. A lot of times what you think is going on may not actually be what's happening. So by drawing it out, it helps to remove any confusion we could have about what exactly points to what and what's going on for each line of code. So please draw out references for these types of problems. Same rules. The underlying code has just been executed, and the code that we ran in main is in red, while the code in functions called by main is underlined in blue. Let's move this here. Great. So initially, all this code is taking place inside of a class called mystery. And we have a main method and a mystery1 and a mystery2 method. So at the starting point, we have created a variable called x with the value of 1 in main, and an array of size 2 also in main, and with the reference to that array stored in the variable a. And remember, when we create an array, all the spots in that array, or indices, hold the default value. And the default value of an integer is just 0. So a will point to a link to an array with a 0 in each index. Now, if we move on to the next line of code, we call mystery1. Mystery1 takes place in its own scope with parameters x, which is an int, and an int array list. And we call mystery1 from main by passing in values stored inside of x and our array a. So like the reference semantic review, the x inside the mystery1 will receive a copy of the value stored inside of the x in main. So x in mystery1 will just store 1. While, since we passed a reference into mystery1, the list parameter inside of mystery1 will now contain a copy of that reference, not a copy of that array. And that reference will point to the array that we created in main, the same one that a points to. Now, if we increment list of x by 1, we'll see that this changes the array list points to, which is the same array that a points to, and now our array holds the value 0 and 1. Now, if we increment x by 1, we increment mystery1's x, but the main's x remains unchanged since these are primitive types and not references. And finally, we print out x, which in this scope is mystery1's x, and the array, the result of calling arrays.toString on list, which is this array that both of our array references point to. So we will output 2 and 0 and 1 for our array toString. Going back to main, now we output x and arrays.toString on a. X is still 1 since we never changed main's x, while our array is the same array that we just printed. So we'll print 1 and 0 and 1 for our array. Now we decrement x in main, so x is now 0, and we set a of 1 to be a.length, or 2. So now our array is 0, 2. And we call mystery1 again. So mystery1's x receives a copy of the value inside of main's x, 0, and list once again points to the same array a points to. We perform the same operations, incrementing list of x by 1. So now our array is 1, 2. And we increment mystery1's x by 1. So now mystery1's x is once again 1. So now we print 1 and then our array 1, 2. Now we print x, or main's x and main's array, which is 0, 1, 2. And we call mystery2. Mystery2 also takes in an int x and then int array list. And we pass in the same value. We pass in x's, the value stored inside of main's x, to mystery2's x, and the same reference, or a copy of the a reference, into our list. So list once again points to the same array in main. Now we set the list reference to point to a new array somewhere in memory of size 2 that contains x in both indices. So this list references an array containing 0, 0. Now we just print out mystery2's x and that array that list references. So we'll print 0 and then 0, 0 for our array. Finally, we print out main's x and the array referenced by a, which is 0, 1, 2. Cool. Let's move on to generics. So depending on the quarter you took CSE 12X or 14X in, you may or may not have learned generics. So this review will keep that in mind. But essentially, generics allow a single class to work with many different data types. We do this by defining one or more, if necessary, generic types in our class declaration, and we can refer to that same type throughout our class implementation. Essentially, it's just a placeholder for the type a client passes in to our class when creating a new instance of our class. It's the type the user passes into what I call the wakas, or the diamond brackets, when creating a new object. We've already worked with generics with all the data structure work that we've done in intro, right? A list, for example, is a generic class. If we wanted to create an integer list, we would pass in an integer into the wakas. Or if we wanted a string list instead, we would pass in the type string into the wakas. We can make a class generic by adding wakas next to the class name in the class declaration, then adding a generic type name inside of the wakas. An example generic class declaration is below. If we wanted to make a new generic class called my generic class, we would create the class declaration like normal, and then add these wakas with a generic type inside. I chose to name my generic type uppercase T, but it can really be anything, right? If I wanted to make this really clear, this was like type name, I can make this generic type name in all caps, and it's still work. But by convention, we like to use T for type. Keep things really succinct, but it can be anything. Now we can refer to this type T throughout our class. And it's just a placeholder for the type a user passes into the wakas when creating a new instance of a class. It's really cool and makes our classes much more flexible. Now let's look at a slightly more complex example. Suppose we wanted to create our own array list. Let's call this my array list. We wanted our my array list to be generic. Like we saw in the previous slide, we can make our class generic by adding the wakas with a generic type name next to our class declaration. And why this is so powerful is that now we have a placeholder type for the type a user passes in while creating a new instance of our object, and we can refer to that type throughout our class implementation. Now let's say we wanted to implement our myArrayList with two fields, a data array and an int size. So size will be the size of our myArrayList, and we could represent this with int. But our data array will be an array of type T, or whatever type the user chooses to pass into myArrayList when creating a new instance of myArrayList. This is really cool because now data can be an array of anything, whatever the user wants. And this also makes our class so much more flexible. Whoa, generics. Let's move on to the last practice problems of this section. Go to your worksheet and attempt problems 1.2a and 1.3a, where you'll be implementing a remove front method for a myArrayList implementation and a generic myLinkedList implementation. Once again, pause the video, and I will go over the solutions as soon as you're ready. All right, let's go over the solutions. First, let's go over problem 1.2a, myArrayList remove front. So suppose this was the initial state of our two fields, with data being this int array and our size being 7. Once we call list.removeFront, for example, with the argument 4, then we would remove the first 4 elements from our data array and set the size to our initial size minus 4, or in this case 3. And remember that we're implementing the myArrayList data structure. So we need to remember to update all of our fields and states. A really common bug you're going to encounter is forgetting to update one of your states. And for me personally, that was size. There have been many times where I forgot to implement or change size when implementing a ADT method, and it's caused me so many headaches in the past. So please remember to double check or triple check that you're updating all of your states when implementing ADT methods. It'll save you so many headaches in the future. Great. Let's continue. So let's walk through what remove front of 4 should do, or what the solution is going to be. So we want our array to contain valid data in the first size minus k indices. Or in our example, since our initial size is 7 and our k is 4, we want our array to contain valid data in the first 3 indices. So what we're going to do is we're going to start at index k, or whatever the first valid value it was going to be in our new array, and move it to the first index. Then we're going to go move to our second valid value, move that to our second index, or index 1, and continue until the first size minus k indices contain the valid values of our new or updated array. Notice how the first 3 values are now 42, 3, and 8, and this is what we want. We don't care about the remaining elements in data because we'll update size to represent that our myArrayList only contains 3 values. It's kind of like hiding the remaining values that we don't care about from the user, and the user won't care because they're not aware of the underlying implementation. It's really cool. So by reducing size, we're kind of just removing the rest of the elements from the array. Even though they're technically still there, um, once we add new elements, they will be overwritten. Awesome. And here's a blurb that repeats what I just said, but in a little more detailed way. So pause the video and read that if you wish. Here is the coding solution. And notice that there are just two parts. The first part is the for loop, which performs the copying or moving of values, starting at the kth index of our data array to the very end of the array, and moving them to the first size minus k indices. The second part of our solution is subtracting k from our initial size. This is how we update our size. Remember to always update all of your states. Let's move on to our second problem. Problem 1.3a, my linked list remove front. Awesome. So just a reminder, my linked list is a class, a generic class with a single front field. And then inside of our my linked list, we also have an inner node class that contains a data and next in each node. Or we have two fields for our node class. And now suppose our my linked list contained the following values, and we wanted to call list.removeFront with the argument 2. In this case, we would want to remove the first two nodes or values from our my linked list so that only the last two values remain since our list is of size 4. So after calling remove front, our front or the front of my linked list would point to the values 91 and 2 with the first two nodes or values removed. And since we only have one state to keep track of, we only need to make sure we're updating front when appropriate. No other states to worry about. So how do we do this? Well, we just need to advance front to point to the right node, and in this case, the 91 node. There are a few ways of doing this, but one way is by creating a cur reference that points to whatever front first points to, or points to the same node as front, and then we set cur to cur.next however many times we need until it reaches to whatever the new front of our list should be, in this case the 91 node. Once cur points to the right node, then we just set front to cur, and we're good. Front points to the correct node, and since nothing points to the first nodes in our list that we wanted to remove, Java's garbage collector will automatically remove those nodes from memory. We don't have to worry about cleaning anything up. Super cool. And now our list contains our desired values. And here's the coding solution. In this case, we set cur to be whatever front points to, and then we advance cur by setting cur to cur.next k number of times. And then finally, we set front to cur. One other way of doing this would be using front is equal to front.next k number of times. And that way it kind of takes care of everything in fewer lines of code. But whatever is more intuitive to you, please go with that. In that section, for further practice, complete the rest of the problems on the worksheet, and we'll see y'all in lecture. Have a good one.